Hi everyone, my name is Isra Akhtar, and today I will be walking you through what my team, Beyond Accuracy, has been researching over the past couple of months. Alongside my colleagues, I would like to start by giving you a brief introduction to our research claims. Artificial intelligence is increasingly used in healthcare, but many screening models rely mainly on clinical and hormonal data and may overlook important factors like metabolic dysfunction and chronic inflammation. This is especially relevant for polycystic ovary syndrome, otherwise known as PCOS, which is a highly heterogeneous condition that affects 8 to 13% of reproductive aged women worldwide. Because patients with similar symptoms can have very different underlying metabolic and inflammatory profiles, AI models may perform differently across patient groups. Using data obtained from the AnyChains database, we developed two logistic regression models, one using hormonal and menstrual features only, and another that also included metabolic and inflammatory markers. We hypothesized that the second model would improve both diagnostic accuracy and fairness across racial and ethnic groups.
For data preparation, we used 10 publicly available datasets from the 2017 to 2018 National Health and Nutrition Examination Survey Cycle, covering demographics, reproductive health, hormonal and metabolic lab values, and various social determinants of health. Each dataset was cleaned individually in Python where variables relevant to PCOS risk were kept, and missing data was handled on a per variable basis. Once cleaned, the datasets were merged in RStudio using a shared respondent ID, and as the only file filtered to reproductive aged females, the demographics dataset was used as our base for merging. Any missing data in the logistic regression models was handled later through listwise deletion. After merging, our final analytical sample was 1,228 reproductive aged women. We also analyzed a GeoGene expression dataset comparing granulosa cell microarray profiles from 3 PCOS cases and 3 controls, providing biological context for the hormonal markers we used in our Rotterdam criteria proxy. Given our small sample size, findings here are exploratory and hypothesis generating rather than confirmatory.
Hi everyone, my name is Tahrim Sheikh. Since NHANES lacks a direct PCOS diagnosis variable, we approximated it using the Rotterdam criteria. If women met at least 2 of the 3 criteria, they were classified as high risk for PCOS. This included irregular or absent periods, testosterone above 70 nanograms per deciliter, AMH above 2.5 nanograms per milliliter, or LH above 7 international units per liter. This left us with 298 high-risk cases, 444 excluded, and 486 low-risk cases. We then trained 2 binary logistic regression models in R. Model 1 used hormonal and menstrual features only, while Model 2 added metabolic and inflammatory markers. Missing data was handled via listwise deletion, and fit was assessed using AIC and residual deviance. Significance was evaluated using Wald Z-test with a p-value threshold of 0.05. Model 2 coefficients were then deployed as a public Shiny app, outputting personalized PCOS grid score that showed a percentage and a category as low, moderate, or high. Our key findings are presented in 3 parts: model performance, exploratory data analysis, and transcriptomic analysis. To begin with model analysis, Model 2 used fewer observations than Model 1. Model 2 had 354 observations, while Model 1 had 777 observations. This reflects a healthcare access disparity that is worth noting. Table 1 also shows that Model 2 substantially outperformed Model 1. AIC dropped from 984 to 279. Residual deviance dropped from 966 to 233, both indicating that Model 2 is a much better fit when metabolic and inflammatory features were added.
I'm Marisha Baig, and I will be talking about our exploratory figures. These 6 plots show how key PCOS-related markers vary across racial and ethnic groups. Period regularity was highest in non-Hispanic Black and non-Hispanic white women. Testosterone was highest in other/multiracial women. Most importantly, Mexican-American women show the highest median fasting insulin and among the highest HSCRP inflammation levels, both metabolic markers that Model 1 completely ignores. The poverty tier plot further shows that Mexican-American and non-Hispanic Black women had the largest proportions living below the poverty line. Together, these patterns show that excluding metabolic features from a diagnostic model risks underserving the groups that need equitable care the most. Finally, our transcriptomic analysis using GEO dataset GSE114419 found that 163 transcripts were upregulated and 68 were downregulated in PCOS granulosa cells. However, no transcripts reached statistical significance after FDR correction, which we attribute to the very small sample size of 3 per group. These findings are therefore exploratory and hypothesis generating rather than confirmatory.
Our key takeaways show that adding metabolic and inflammatory markers reduced AIC by 72%. This confirms that Model 2 is superior. Though only menstrual regularity, testosterone, and LH reached significance, metabolic markers revealed a meaningful racial variation that a hormonal-only model would miss. For example, Mexican Americans showed the highest fasting insulin and HSCRP, while non-Hispanic Asians showed the lowest. Transcriptomic analysis identified 163 upregulated and 68 downregulated transcripts in PCOS granulosa cells, though none survived the FDR correction, leaving these findings exploratory.
Everyone, my name is Jenna Ayash, and today I'm going to be talking about the interpretations and future directions of our project. For the interpretations, the study demonstrates that incorporating metabolic and inflammatory markers into AI-based PCOS screening substantially improved overall model fit, as shown by the large reduction in AIC from 984.59 to 279.73. While menstrual regularity, testosterone, and luteinizing hormone remain the only statistically significant predictors, we found that metabolic and inflammatory markers varied considerably across racial and ethnic groups. This is important because it suggests that AI models relying only on hormonal markers may appear accurate overall while still overlooking important subgroup-specific differences. We also observed differences in poverty across racial and ethnic groups, indicating that socioeconomic factors may influence both PCOS presentation and access to the laboratory testing needed for comprehensive screening. Our exploratory transcriptomic analysis further supported the biological heterogeneity of PCOS by identifying distinct patterns of gene expression, although these findings require validation in larger cohorts because of the limited sample size. Overall, our findings suggest that AI models should be evaluated not only by their overall predictive accuracy, but also by how fairly they perform across diverse patient populations. Incorporating biological, metabolic, inflammatory, and socioeconomic factors may help reduce hidden bias and lead to more equitable and clinically meaningful PCOS screening tools.
In summary, our study shows that AI-based PCOS screening models benefit significantly from incorporating metabolic and inflammatory markers alongside hormonal features. Model 2's dramatic improvement in FIT, with a 72% reduction in AIC, confirms that a hormonal-only approach leaves important clinical information on the table. Crucially, the racial and ethnic variation we observed in metabolic markers like fasting insulin and HSCRP highlights that overall model accuracy can mask meaningful disparities in how well a model serves different patient groups. While our transcriptomic findings remain exploratory, they further support the biological heterogeneity underlying PCOS. Moving forward, we hope this work contributes to a broader conversation about building AI screening tools that are not just accurate but equitable, tools that work for every patient, not just the average one.